Welcome to the semi-learned lecture that explains Amdahl's Law. This very simple law of computer architecture was created to warn us from doubling down on parallel processing. But ironically, it is now used for the opposite reason, to help us get more performance out of parallel processing for AI and machine learning workloads. Now, to keep things simple and without a lot of computer jargon, we are going to explain how Amdahl's Law works by trying to move some boxes from a factory to a store that is located across town. Imagine that you manage a factory that produces very high demand product, and that you package these products in an attractive green boxes like the ones we see here. To make money, you need to sell this product in your store that is located on the other side of town. Your product is in such high demand that you cannot restock the store shelves fast enough. So you must find a way to move the boxes from the factory to the store as quickly as possible. And this is when Amdahl's Law comes in. And even though Amdahl's Law was created to speed up computer software programs like artificial intelligence, Amdahl's Law is perfectly suited for this less technical scenario. So let's demonstrate how Amdahl's Law can help us move these boxes quickly from the factory to the store. Starting with the naive solution, you can buy a van, and then you can dedicate one of your employees to load up the boxes into the van and then drive the van across town and then unload the boxes in the store. Soon after you do this, you find out that the factory can make boxes much faster than your employee can move them to the store. So you go ahead and you hire a second worker to help. Now the question is, how much faster will two workers be when it comes to moving the boxes? To answer that question, let's look at the duration of each of the subtasks. Let's assume that it takes one worker 30 minutes to load the van, 40 minutes to drive across the town, and another 30 minutes to unload the van at the store. Of these three tasks, only the loading and unloading will benefit from adding a second worker. We call these types of tasks parallelizable because their duration will shrink when multiple workers are completing them, working together in parallel but on the same task. The duration for driving the van between the factory and the store is of course not impacted by adding more workers. Tasks like driving that van are not parallelizable and are therefore called serial. Serial tasks need only one worker to be active, and any additional workers will be idle while the van is being driven from the factory to the store. So let's add that second worker and revisit the task durations. The loading time will now go down from 30 minutes to 15 minutes, and the same thing is going to happen with the time to unload the van. The time for the drive is not changed by adding the second worker who's being paid but not really doing any useful work. In other words, they are overhead while the van is driving along. And in return for doubling the number of workers, the overall duration has now dropped from 100 minutes to 70 minutes. So we spend double the money on worker wages, but our duration does not reduce to half due to the serial portion of the task that does not change no matter how many workers we add. And unfortunately, the more workers we add, the less incremental benefit we're going to get. What is happening here is a perfect example of the law of diminishing returns. And we can see that law of diminishing return by plotting a graph where the y-axis is the duration of moving the boxes and the x-axis is the number of workers. We already saw that doubling the workers reduced the duration by only 30% from 100 minutes to 70 minutes. Now let's keep adding more workers and see what happens to the graph. By the time we have 5 parallel workers doing the loading and the unloading together, we are barely down to 50% of the original duration of time. And if we boost the number of workers to 10, we only get to 46% of the original time. And if we further boost the number of workers from 10 to 15, we only get a meager 2% additional reduction in the overall time to 44 minutes. Apart from being a great demonstration for the law of diminishing returns, this example gives us a very important conclusion of Amdahl's Law. The 40-minute drive of the van, that is the serial portion of the problem, sets a floor for the minimum duration that we could ever achieve, no matter how many workers we add to the parallel portion of the task. Now, of course, there is a formula for Amdahl's Law, which is the mathematical representation of this curve of diminishing returns. The formula calculates the time t it takes to complete the task as we add more workers. If the time to complete the task when we only had one worker is represented as t sub I, or the initial time, then Amdahl's law tells us that the duration t when we increase the number to n workers is the initial time multiplied by this rather complex looking factor. The equation is actually not that complex. The symbol p is the percentage of the initial duration t sub I that can be parallelized, and the symbol n is the number of workers. So the term 1 minus p represents the serial portion of the overall duration that is not impacted by the number of workers, whereas the second term is the remaining parallelizable portion of the task after we've employed n workers to reduce that duration. You will notice that when the number of workers is equal to 1, then the formula predicts that the completion time t is equal to the initial time t sub I, which is what we would expect. Now, in many books and websites, Amdahl's law is expressed in the form of a speedup, which is the initial duration over the new duration once we've added more workers to accelerate it. If we substitute in the formula for the new duration into this simple equation, then we will get this formula for speedup. Now, it turns out that the formula for Amdahl's law is usually a little bit optimistic. In real life, numerous real overheads appear. For example, workers may slow down as they try to coordinate the work amongst themselves. And so the time to move the boxes will generally be longer than what the white line predicts. But the formula is still very useful in illuminating some important conclusions about adding parallelism into any system. The first conclusion from the formula is that the first few parallel workers gives us the most acceleration, with follow-on workers resulting in diminishing returns or benefits from parallelism. The second conclusion is that no matter how many workers get added, the duration of the serial task puts a hard floor on the minimum duration that we can achieve. Here, the serial task of driving across town takes 40 minutes. To get below 40 that 40-minute floor, we must reduce the time of the serial task. Now, there are many ways to do this. We could route the van through a toll highway between the factory and the store. This will cost us some money, but if we can halve the duration of the serial task, then the floor will drop from 40 minutes to 20 minutes. In computer systems, this would be equivalent to running the processor at a higher frequency to complete the serial task sooner. Alternatively, we could have found a better shortcut through the city streets that avoids congestion and thus reduces the transit time. In computer science and computer system terms, this would be equivalent to inventing a new algorithm for the serial task so that it does not require as much time to complete. In either cases, Amdahl's law tells us that the parallelism only helps for the parallelizable portion of the task, and that eventually we must work to reduce the duration of the serial tasks if we're going to get any additional speed up. And that was the key point that Amdahl was trying to make when he formulated his law in the late 1960s. That at some point, adding more parallel workers just does not help much more, and one must start to reduce the duration of the serial task. The ability to accelerate the serial portion by a factor, which we are going to call A, means that we should amend our simple formula to include that the serial duration can itself be sped up by some method that is not parallelism. And the third conclusion of Amdahl's law is that when the serial task is shorter, that is the orange line, the impact of adding parallelization becomes more pronounced than effective. And this comes as no surprise, because if the overall time was dominated by the parallelizable portion, then adding more parallelism will have a significant initial impact on reducing the overall duration. And because Amdahl's original intent was to make engineers focus on the serial portion of the task, Amdahl used his law to guide engineers on how to optimize workloads that were made up solely or predominantly of serial tasks that cannot be parallelized. For example, say we have a workload that is made up of two serial subtasks. Task A, which lasts for 30 minutes, followed by task B, which lasts for 40 minutes. That gives us a starting point where the overall time is 70 minutes. To increase the throughput, we naturally focus on the slower task first, and that is task B. And we're going to take successive actions that make it faster. For example, we can execute task B on a faster machine, or we can invent incremental methods that will complete task B in a shorter time. And we immediately see here the same shape of Amdahl's law. As we accelerate task B, the unaccelerated task A represents a floor for the final time. And that means that we cannot just focus solely on the longest subtask or the subtask that is easiest to accelerate because of the curse of diminishing returns. Instead, we've got to reduce the duration of all serial subtasks to avoid the curse of diminishing returns. Which gets us to the modern day irony surrounding Amdahl's law and how it's used in artificial intelligence. For when Amdahl created it in 1967, he wanted to guide the computer hardware designers away from their fondness with parallelism as a miracle solution to performance problems, because, as we found out, it suffers from the curse of diminishing returns. And Amdahl was really successful. For over 30 years, the computer hardware industry focused on making serial tasks faster by increasing the speed of processors and also by inventing many hardware circuits that sped up computation. But in 2003, and for many reasons that are beyond our current scope, the performance of computer hardware could no longer be improved significantly for serial tasks. And so the hardware designers started creating parallel systems in the form of multiple CPUs on the same chip, hoping that the software writers will be able to use this parallelism to accelerate software. At that point, we started seeing silicon chips with 2, 4, 8, and even more parallel CPUs in laptops, desktops, and mobile phones. In 1912, Alex Krizhevsky, the inventor of AlexNet, demonstrated that artificial intelligence software can be written in a way that makes its execution time dominated by parallel tasks. He then used tens of parallel processors that just happen to exist in common GPUs to make AI tasks really fast and therefore practical for everyday use. And so ironically, Amdahl's law is now used on a daily basis to guide engineers on how to use parallelism effectively instead of its original intent to steer them away from parallelism. And so naturally, the next topic to explore will be how does parallelism work in AI workloads? And we're going to do just that in our next presentation. You're going to find the link in the description box below once the video is uploaded to the website. Thank you very much and best wishes to you.